welcome everybody. Thanks for joining us today on stage. We're going to be presenting to you transforming the transport data by integrating spatial and aspatial data. My name is Shanuka Baysena, and this is my colleague from Databricks, Danny Wong. So, right at the end of the conference, so really enjoying having you guys here. For me, for us, data is definitely the key for unlocking our future. And you will hear this everywhere. It might sound like a buzzword. It's something that I truly believe in, and that Databricks has really helped us through our journey unlock the foundations that we need to have with everything that we do. So, transport as a domain. Within the public sector area, we look at a lot of different data sets. So we manage things from trains, buses, like public transport modes, to private modes, cars, micromobility, it could be scooters. You can have freight if you're trying to move goods and services around, it can be from your ports. And it's really, really important that we provide a view of how information moves through that environment, whether it's in real time, to really get an understanding of what the domain is trying to do. So if it is, whether we're trying to manage traffic, improve infrastructure, transform how we move people from domain to domain, we really need to ensure that the data is available, it's accurate, it's complete, it's consistent. So it can be a challenge in the public domain. We tend to go through various cycles of what's important to a government and what's not. So that shifting landscape can impact how we deliver our services to our clients. And that you will see that a lot within the data that we work with. There are definitely challenges, but through the innovations that we get through Databricks, through the capabilities, we can start to simplify and amplify the capabilities that we get. The main reason why we're here. So data in many ways exists in silos, and this is something even Ali mentioned at the keynote. And democratizing data is very, very important. And there are many ways to look at data. You can cut it up in many different ways, but we talk about it as aspatial and spatial. So aspatial data, if we talk about it, it's things that don't have a geographic context. So if you're talking about a bridge can be made up of very different components. It can be made up of nuts, bolts, wires, it can have bitumen, road, various different things that comprise it. And this can be the aspatial data of that view. The spatial data can relate to a 3D model of that of the bridge. So you can actually visualize how that bridge is constructed and made. But in addition, it can be a line that's represented on a map to say, all right, this is the bridge, and this is something that's associated with it. But it can be more granular than that. It can be multiple lanes. It could be a walking lane. It could be a bus lane. It could be a road. So there are various relationships that we have between both spatial and aspatial data. Within the transport domain in particular, and it's true for many domains, we understand the world through the spatial lens. That's where we can derive a lot of correlation or a lot of information, and we can make decisions around what will impact our network. So if I want to understand how many cars are going on a particular road, that is just one layer that tells me congestion. It can tell me the average speed. That's another visualization, right? There are various bits of information that we'll gather from that. So you've probably seen similar slides to this before. The only thing we really sort of wanted to call out here is that spatial and aspatial data, if you've got platforms like Esri or various other spatial tools, typically they will exist in their own silos. You've got spatial analysts and spatial engineers who work with them, they really understand them, and typically they're in proprietary formats. It's very hard to move them in, and it's very hard to get information and analysis from them. So what we wanted to explore with Databricks is how do we bridge that world, bridge that gap, simplify and bring spatial into the aspatial world, right? So you do not need a spatial engineer or a spatial analyst to make sense of it. You don't need a spatial engineer or a spatial analyst to integrate that data, right? The other thing is there's cost implications to even processing data. So when we think about it at the end of the day, spatial data is just data. We've got to make sure that we're processing it in the right platform. So is the cost of bringing your data into your spatial environment correct? Is it too high? Can we do that job better in our data platform, right? Is it appropriate? And sometimes, you know, the buzzwords can be like, you know, standing here with Databricks, like, hey, move everything into the data platform, but that may not also be the best outcome. We might have to choose our spatial platform over our data platform. So really making that differentiation. We want to make sure that our data scientists, our data engineers and ML engineers, alongside our GIS analysts and our business users, have access to spatial intelligence. That is very important. And that can be correlated by bringing all these data sets together. I'm just going to quickly go next one. There are a lot of different libraries available, whether it's Sedona, GeoPandas, Raster AI, H3, we've got Esri, Safe Software, Cardo. There's many things available within the market to enable this journey. The question you have to ask is, what is the right tool? Should I be processing it in the data platform? And if I am, what value am I unlocking for that data set and other data sets once you start to correlate them together? Today, we're going to focus heavily on just the Databricks spatial capability, right? What's within that tool set. So why Databricks for spatial? So I think I kind of alluded to it before, is that the cost of processing your data, bringing it into the platform, we need to make sure it is as low as possible, right? There shouldn't be any friction to moving data into your environment. If I had to bring a workload, if I think about the current environment I'm in, if I had to bring a complex geospatial workload, I would have to use potentially a tool like Safe Software to do the translation and then put it into Esri as a spatial platform, and then I would need to move it into a data platform. And that can cost a fair bit of compute, time, processing power, and it's just not effective. Through Databricks, certain tasks are more efficient and more cost-effective. It can be quite flexible when you introduce the governance and data quality that you can build into it. You can do more than just one task. You're not just doing a spatial task or an aspatial task. You are doing it all together, and you're finding ways to unlock that value quicker. So we're going to cover 4 different use cases today, just to give you a flavor of what what's possible with Databricks Spatial, and why you should consider bringing that information into your platform and what it can really mean. So let's talk about the first one, laying the foundation. So we have a process where we work with OpenStreetMaps as one of our base map foundation layers. OpenStreetMap is great. It's used by many organizations around the world, but it has data quality issues. It has gaps. It has wrong information. So for us to be able to utilize that data, we are looking at different ways to augment, uplift, and manage that capability. There's a library called Overture that's contributed to by Facebook and Google and a few other organizations to improve that quality. So the first thing that I thought about is, how do I bring this data into my environment and understand, first of all, what's in it, what value can it unlock, and should I even utilize it and integrate it with my capability? I could do that with spatial tools. That's the standard process, right? Get a spatial engineer, figure out what that file format is. It comes in GeoParquet, so it's not going to easily go into some of our target systems. We will have to do some transformation. It's also a very large file, 356 gig. So processing that in our spatial platform will take a long time, cost a lot of money, take a lot of time. So it was probably about 5 to 10 days worth of effort just to get this through a spatial thing. Speaking to Danny, saying, hey, what I really want is, I want the overture maps. I don't want the entire world. I really just want Victoria as my boundary, right? So they will cut down the data set a lot. And I want to add the H3 index to that so that I can start exploring this data set. What do you think? Can we do it in Databricks? Of course. Danny said yes. So the purpose of this is just to show you that we've got a number of different contributors to Overture. We get OpenStreetMaps. We want to be able to blend the data sets together and figure that out. I don't want to process 356 gig worth of data because the rest of the world, or even the rest of the country where I live, it's not really relevant to our use case, right? So we need to be able to do that quickly, unlock the value. The H3 index helps us with correlating things very, very quickly. But yeah, that's that. So the process was pretty straightforward. I think within a day, Danny was able to have a look and say, all right, yeah, this is something we can definitely do. GeoParquet was the file format. So we were able to actually bring that easily into our data platform, right, and start to massage that. So the longest time it took was, what is the Australian boundary or the Victorian boundary? Like, what is the polygon shape so that we can filter the data in a meaningful way? The other thing that was really cool was, well, when I first thought about this, I'm like, oh, let's just do this for Australia. But with the parameterization, we're able to simplify that to say, well, if you change your mind, if it's going to be based on Victoria as a state boundary, or you can pick it at a more local level, or a postcode, whatever you choose, it's very easy to change the filtering criteria. You don't have to go through, update the code. This is something that's reusable for us. We can share that with other departments if we really wanted to as well. So very simple ways to ingest that data. We have a single notebook that's ingesting the information and then starting to categorize all the parts that are within it. So within that Overture file, it's not just the geospatial network, the underlying base network. There are other features, points of interest, waterways, things that we may or may not care about. So the first exploration was, well, what is relevant to us in our context in the first instance? Should we just bring it all? Or should we just bring parts of it that's relevant? In this instance, we brought it all because we were already able to get it from 356 gig down to less than 1 or 2 gig. So, cost of processing. Now, the cost is quite small, and if I wanted to speed it up, I can add more workers. We didn't do that in the version that we started with. We're happy to start with an hour plus, but this is the power that we have with processing these files. If I had to do this in an alternative process, it would have not only taken me longer to build, longer to develop, it would have been harder to scale in our environment. Now, that may not be true. You might be in the audience thinking, oh, I could do this with this spatial tool. It's very easy. I can do this, this, and this. Sure. But if you have the need to bring that data into your spatial platform and your data platform, right, you need to think about where you're processing it. Are you processing it more than once? Do you even really need to? So in this instance, we spent, let's just say 7 cents, 10 cents, right? We've cut down the size of the file to the Victorian boundary, the points of interest that we care about, and that can then be shared to our spatial platform. As this file changes on a monthly basis, we don't have to export the entire file to the spatial platform. We can just send the delta. So that cost incrementally goes down. It's really, really important to consider this because there are many different ways to do get data in, get data out, get information from it. You really need to understand where the value is. Should you process it this way, right? If there's value in processing it at a greater speed, great, do that. So why why did we do this? So the goal of bringing this data set in, first of all, was to understand what value was in there. We were able to do that, turn it around within a day. Really understand there's information in there using native features within Databricks, and that's only going to grow. There are other libraries if you want to do more complex spatial capabilities, but we just need to think very basic things. I can industrialize this process, and it would cost us less than $1 probably every time we try to process it, right? As opposed to and done by a data engineer, no less, not just a spatial engineer, because we get a lot less of those people than we have data people, right? It brings that into the ecosystem that we want. All right, I'm going to hand over the next one to Danny.
Okay, thank you, Shanika. Good day, everyone. So my name is Danny Wong. I'm a solution architect from Australia, Databricks. First of all, it's day 4:16 p.m. now, so well done, everyone. So you are here, probably you are passionate in geospatial, or like you like transport, or you like public sector, or probably you just simply had enough LLM, maybe. So in this, in the following section, I will talk a little bit about other use cases, riding on like what Shanuka just said. So the overture map use case, we ingest the data, we land those geospatial data into the lakehouse, and then now we can start do a little bit of analysis on what we have. So it is a role, that's obvious, and it is simple. So, and as you expected, the next slide, I'm going to tell you it is not that simple. So because like in the analytics itself, usually we will try to understand like different dimensions. So say, for example, like if I want to do some analysis based on speed zones, or based on pavement conditions, or based on accident, then I will have to find a way to segment the roads into different forms and shapes, and then we can apply some like machine learning algorithms, or like we can visualize it. So there are different ways to do it, but I think the very first process is like we have to find a way to very dynamically to slide up that, to segment that row. So this is one example, like if I am trying to segment this row into 2 different speed zones, like 80 kilometers per hour, or I should say mile per hour, because we are in America. So we can also basically split that up into 2 different segments. But it is not that simple, because like, as I said, like there's a lot of different attributes and dimensions that you can segment up the row. So say, for example, like we can have one segment that talk about the number of lanes, like 2 lane, 1 lanes, etc. And we're also trying to analyze like the asset on the road itself. So say, for example, like if there's a bus stop there, can I be able to keep track of like which bus stop are on which route, as an example. And also the form and shapes of the geodata itself will vary as well. Like sometimes it will appear as longitude, latitude. Sometimes it might have a different ways of representation. So we have to cater for that. Other example, like safety wide road barrier, we probably want to know where that is and to have the geometry of that location. And potholes, road crash, speed cameras, those are other examples. And we can also segment that up based on like pavement conditions as well. And as I said, like those geodata are coming from like, coming in different forms and shapes. So one very common way to represent the data is based on measure value or based on chainage. So like this one as an example, like if I want to say, okay, this segment, it is starting from 200 meters from that route, and then it ends at 300 meters. So in that case, I didn't get the exact coordinates, but I just kind of get a relative coordinates based on chainage or based on measure value. So this is another type of common data that we have to handle and unify in the lakehouse. So to solve this problem, usually the approach is go through something that we call dynamic segmentation. So there are other products in the market can do dynamic segmentation, but usually that is not scaling quite well, because in a transport agency, What we are looking at is a huge data set, a lot of different row segments. So if we want to do that at scale, we need to have a scalable platform that can parallelize all this segmentation, and that has to be dynamic enough to cater for changes as well. So because right now we are looking for speed limits, pavement conditions, traffic volumes, but tomorrow I might have to look into other metrics as well. So that's why dynamic is very important. So you can see like point A basically is a point that talks about our vehicle breakdown. Point B, B is not a point, so B is basically a line string on that white line. C is another line string. So basically we have to segment the row in different ways. It could be like a shorter line, or like it could be another point. So before we have this solution on Databricks, as I said, like traditional GIS tools can do it, but when they are trying to handle large volume, they are starting to struggle. And managing and integrating diverse data set for spatial and non-spatial is quite key as well, because like for GIS tools, usually you can answer a lot of questions around the geo context, but what if I want to combine that with other spatial data sets? GIS will be struggle to do that. So that's why like landing on the lakehouse, we can easily combine spatial and non-spatial. It will give us some like additional insights. And handling real-time becoming more and more crucial, because right now I think there's more and more streaming and real-time type of data source, such as speed sensors, roadside cameras, etc. So having a platform that can handle real-time streaming data, that is key as well. So after they run like these use cases on geospatial on the geospatial lakehouse, the functions that they are using, those SE functions that they are using, now basically we'll be able to like scale up to the massive data set, because like the underlying Spark architecture is very good at that. Like we can distribute the load to different workers to handle that in parallel manners. And as you see in the previous example, the cost is quite low as well. Like if you want the process to run quicker, you just simply like run more workers, and then you can like shorten the time of the processing. So this is quite key when we are talking about huge data sets. And also now we got a central authoritative source of truth of data for both spatial and aspatial data. And also I got all the flexibility to combine different data sets to create different views, different reports that I might not able to do that before with the traditional GIS tools. And also, as I said, like there are more and more real-time sources, streaming sources right now. Ingesting those data live in near real time is quite key as well. So this is just one example. Like if we want to try to like cut that long row into a substring, line substring, which is a segment. One way to do it is to use it as the line substring function in Sedona. So I think that shows the extensibility of the platform, because what Shanuka just shared is like we can use the built-in spatial SQL to do all those like polygon filtering, which is pretty good. But for more advanced use case, like if I want additional functionality that is not coming out of the box, we can easily bring in different libraries to get the job done. So in this case, we are using Sedona for this particular purpose. Then we can basically, based on the chain age value, like the starting point and the end point, we will be able to get the line string, which is the geometry as a result. So you can see at the top right is the result that we got. Like when we provide the chain age, we will be able to get the line string as a result. And another example is kind of the other way around. So say, for example, like on a road, we got some bus stop there. So for those bus stop, we know the location, we get the geometry let long, but we didn't know the measure value. We didn't know like how far from that route starting point. So if I got a route here, I got a bus stop. If I want to know like how far that bus stop from my starting point, we can use this st line locate point function again in Sedona to return that measure value for me. So at the top right-hand corner, you can see like basically those measure values are the one that coming out from this function. And we can also visualize that quite easily as well, because I think geospatial data are very visual in nature. So with proper visualization is very important. So on Databricks, you can easily visualize that with the Kepler library, so another open source library. So from there, you can see like we can show the segment. In this case, it is based on the pavement conditions. So with this dynamic segmentation on Databricks, it largely improved the operational efficiency because right now you can run this process in bulk as well as in a very low cost and a lot faster as well. And it also reduced the cost for data management because we are reducing fragments, we are reducing silos by incorporating spatial and aspatial data into a single authoritative source of truth. And it also helped to improve the situational awareness because like now we can ingest a lot of real-time data source, so we have better understanding on the ground what is actually happening right now. So dynamic segmentation is one case, but we also want to see like how we can bring data to life, how we can do a little bit more visualization. And the problem in geospatial visualization is sometimes it might be a little bit overwhelming because you have different dimensions to look at the same thing. So like if you got experience on Google Map, you might want to like turn on, turn off some layers. You probably just want to focus on the problem that you are solving. And in geospatial, in transport, you might have different dimensions, like look at bus stop location, passenger flow, traffic volume. If you overlay everything all at once on the visualization, that might not be super helpful. So let me give you one example. So this is a map that's showing a number of bus stops, and we also have a route right here. So for this route, I want to focus on the bus stop on this route. So I want to remove all the noise that I'm not interested in. So with a data set like with all the routes and with all the bus stop, how I can do the matching, how I can do the filtering, this is the problem that we are trying to solve right now. So one obvious solution is like, because like the bus stop itself is not exactly on the route because the route is for the cars. So usually the bus stop is on the side of the road. So how we can make it on the road? So one obvious approach is like, how about we make the line wider? So this is the straightforward approach. So if we can make the line wider, now the points, the bus stop is actually on the line. So, but there is some complexity here because if you are using functions like ST buffer functions, so usually the input that they accept is something called angular units. So it is expressed in degree. So I think for you, if you want to understand like how much should I extend it to make it wider, it's not very straightforward because the input parameters in this case, I put in like 0.00035. And that is actually converting to like 38 meters. So I think this is not super trivial to do that. It's not very straightforward. So I guess the good thing for this approach is like this is a very common function. So if you use it in other systems, you will feel like, okay, I know what that is. And it's flexible, like you can easily change the input parameters. You can make the row thicker, wider, narrower. So basically, you can do it quite easily. The downside is the performance might not be as good if you are doing huge amount because this ST buffer function is a very computational extensive functions. And the angular units things is a little bit tricky as well. So it's not as straightforward. So that's why like we are looking into another approach, which is the H3 K-ring approach. So if you are not familiarized what H3 is, so H3 is an indexing system that is created by Uber. So they're trying to index the world in heaps of hexagon. So for this K-ring features, basically that means like, okay, I've got a hexagon here. If I say like K equals to 1, then I will have one layer of hexagon around this central hexagon. So if I say K equals to 2, that basically means like I've got 2 layers of hexagon around this central hexagon. So with that, I will be able to find out like if I got a point of interest or if I got a line string, I can easily expand the K value to make that wider. depends on the use case. And also like with this K-ring, the reason it called K-ring is like once you form the ring, it's kind of like approximating a circle. So that's why it called a ring. So we try different values. So yeah, we have to do a lot of like experimentation, trial and error. So the first value that we try is k equals to 4. So if we try k equals to 4, basically none of the bus stop is showing up because that is not overlapping with the ring that we were talking about. So the next value that we try is k equals to 5. And that is not complete because from the visualization, we can only see the bus stop on one side. We can't see the bus stop on the opposite side. So that's why we increase the value to k equals to 7. So now we see both show up. But if we want to run it, we just simply change the number. It's very simple for you to do a little bit of experimentation. What is the optimal and right number? And also because Hex3 is an indexing system, that is a lot more efficient comparing with the ST function. And there's a side note here as well, because I think usually like in geospatial, you might be acquiring different data sources from different providers. And different providers, they might be representing the same thing in a slightly different coordinates. Like they might say the row is in certain coordinates, but the other sources might tell you something differently. So in this case, like if we can visualize it easily in the Databricks platform, it will help you to spot the discrepancy, and you can use it as a data quality check as well. So I think the good thing for Hex3 is that it's very scalable. If you want to do spatial joins, if you want to do K-ring, it's super easy and scalable. And Hex3 itself is very flexible as well, because Hex3 itself, it got 16 resolution from 0 to 15. So you can, based on your use case, to determine how big your hexagon should be. Should you have a super big hexagon for more macro analysis, or you have to got high precision, high resolution, but very small hexagon? So you can choose your own adventure in that case. And the downside is Hex3, because that is an indexing system, that is basically an approximation that might not be super accurate. So, and in terms of integration, it will have a little bit more effort, depends on like what systems that you integrate with. So if that particular system doesn't support Hex3, then you might have to like fall back and then use traditional way to do integration. So that would be potentially a little bit more work. So there's another example just trying to show like if you want to use K-ring, it's very simple. You just have to simply specify what is the resolution of your Hex3 at first. We didn't show that here. And also like the ring size, like in this case, k equals to 7. So you can just simply change the numbers and then you can do different experimentation. So this is the before. It's a little bit noisy. You can see all the bus stop that I am not interested in. And this is the after. So after filtering out, I only show the bus stop along that route. So yeah. So with this approach, we find it provides a little bit better data quality assurance because we can visualize it on the visualization. It also helps to do smarter infrastructure maintenance as well, because we can do all this proximity analysis. And also like it helps from an accessibility standpoint as well, like with all this, answering all these questions. So yeah, I know like although you all in this section, your heart still like to listen to some LLMs, right? So I will cover a little bit. So these are some other experiments that we did with the geospatial data. So in this case, we are using this DBRX model, the Databricks open source model, in combination with a function called AI query. So what we are trying to do is to democratize the way for different personas, different people to access and use large language model. So AI query is a SQL function, which basically means if you are a SQL analyst, you can easily trigger, invoke, and use the power of large language model. So what we are trying to do here is like we got a data set. This is a disruption data set. I would like to get some basic analysis, try to understand what data that I've got. So in the AI query prompt, what I simply tell DBRX is, okay, can you look into my data set? Can you try to give me 5 bullet points, which I should know, and summarize it? And most importantly, you have to talk about your points based on the data that I provide to you. So in this case, it just gives me some highlights. I can easily embed that into a dashboard so that like before I drill down to any visualization, I can easily look into this as an executive summary. So I basically know like what is happening within my data sets. And the other use case is around Genie. So Genie, as you see in the keynote, basically that is a tool that democratize and open up the data access to less technical users. So in this particular case, if I got a disruption data set, if I want to ask questions like, okay, which area, which suburb has the highest number of disruption over a period of time, in that case, I can ask those questions pretty easily in layman questions languages. Okay. So with that, I will hand over back to Shanuka. Thank you.
Look, thanks, everyone. So I think the key takeaway for us, the thing that we really want you to walk away today is integrating spatial and aspatial data so that it's just data, right? We want that data to be democratized. And you don't know what the question is that the person is going to ask. You want to make sure that you give everything that you can to integrating, allowing the data to be correlated so that people can make decisions, people can ask questions that you haven't necessarily thought of. You don't need to be in a spatial system or a data system to do this, right? If you can actually democratize the data, you can actually simplify that. So for me, the call to action is if you think you have spatial data or if you're not sure, have a look within your organization. What questions would you have from your data? What correlations can you make? If it's in a transport context, we want to lower the disruptions. We want to understand the impact of road crashes because the road hasn't been maintained. Is it another reason, right? What is causing this? Is it a speed sign, speed zone issue? So if you can bring the data together and you can eventually call it just data, it doesn't matter if it's spatial or aspatial, you will be able to start to unlock value. Connecting it to democratizing AI, that's the next step, right? Once you've got everything there, the correlations are created. H3, as an example, will allow you to connect the dots. You can think of your spatial data as multiple layers of a cake, right? You might be only interested in asking questions of one of those layers, but other people might want to combine 2 or 3 of them to get a different answer. And that's what we really want you to be able to do. So, hope you enjoyed. Thank you very much.